Hello and welcome to this podcast for Radiation Physics for Wenatchee Valley College. I am Todd Bussey, your instructor, and I hope you find this podcast and all the other podcasts for this class helpful. Today we are going to discuss Chapter 2, which is Radiation Concepts. The first thing that we're going to discuss is matter and energy. So let's do some vocabulary. First of all, we have to look at matter. Matter is anything that has mass and occupies space. We can also think of matter as having energy. When we get to Einstein's law of energy, we have energy equals mass times the speed of light squared. So matter is just what stuff is there, how much stuff is there. When we look at matter, we also have to look at mass. And mass is a property of physical objects which measures the amount of matter the object contains. Since we're a metric country, and we are a metric country, we're going to measure most things in kilograms. Although, since you're in the real world, you will also still measure things in pounds. But I'm a physicist, and so we measure things in kilograms. So mass is just kind of how much stuff is there. And then we have to look at weight. Weight is the vertical force exerted by a mass as a result of gravity. And in the metric system, we measure weight in newtons. In the customary units, the one that we're used to, we actually measure mass in slugs and weight in pounds. So when you step on a scale, you're actually measuring the force of gravity that's pulling down on you. That's the weight. And weight and mass are different. You have the same mass no matter where you are, unless you lose a limb, but you have the same mass no matter where you are, but your weight is different. So if you actually want to lose a little weight, take a scale up to the top of Mount Everest and weigh yourself, and you'll have less weight there because the pull of gravity is less on the top of Everest. So mass and weight are different, and we have to remember that they are different. The next thing that we have to look at is how we put all of this stuff together. We have mixtures, we have substances, we have elements, atoms, compounds, molecules. They all fit together. The first one that we are going to look at is the atom. The atom is the smallest component of an element having the same chemical properties. So that's like an atom of oxygen or an atom of carbon. All carbon atoms behave the same way, so that's going to be an atom, the smallest thing that we have. At least for what we think of as the smallest thing that we have. There's a lot of other theories out there. Molecules are another thing that we're going to deal with. A molecule is the smallest particle of a pure substance that still retains a chemical composition and properties. Molecules can be either polyatomic or monoatomic. The polyatomic ones have more than one element attached to them, like oxygen is usually O2. There's two oxygen atoms stuck together, two oxygen elements stuck together. Or monoatomic, there's only one there. Like some of the noble gases are monoatomic. And then after we have molecules, we have to have compounds. Compound is a substance formed from two or more elements with a fixed ratio determining the composition. And the ratio is dealing with whole numbers. When we look at a compound, we're looking at water. Water is a compound. It has a hydrogen and oxygen attached together. So it's H2O, two hydrogens, one oxygen, and they come together to make a compound. So one way to look at this is all compounds are molecules, but not all molecules are compound. So you can have a molecule that is a compound, like water, and you can have a molecule that is not a compound, like oxygen. O2 is a molecule, but it's not a compound. Okay, and we have a picture of a water molecule there. So we have two hydrogens attached to an oxygen. That's going to be a compound. Right, the next thing we're going to look at is you need to be familiar with the periodic table. So there's a link to a periodic table on the website, and I would look at that, be familiar with that. If you've had chemistry, you are familiar with that. We're not going to go into as much depth as chemistry does, but you have to know the basics of the periodic table. And it's also always helpful to have one handy, so if you go to the bookstore and find a periodic table. That might be handy for this class at times. The next big topic we're going to look at in this podcast is energy. And energy is a fundamental quantity that every physical system possesses. And for us, mostly energy is going to be measured in joules or electron volts. When we get into small amounts of energy, we're going to use electron volts. And energy is basically how much work can be done on the system or by the system. And a lot of times it's heat. We exchange heat between systems, and energy is exchanged in that heat. And there's a whole bunch of different types of energy that we're going to deal with. One of them is going to be mechanical energy. Mechanical energy is the energy which an object possesses due to its motion or its stored energy of position. So wherever an object is, it might have some motion attached to it, so it has some mechanical energy, or it might be above the ground, so it has energy stored because of its position. Another type of energy that we have is potential energy. And potential energy is the energy of a system associated with the spatial configuration. Basically what that means is where it is. The one that we use most often is potential energy gravitational. So gravitational potential energy. And that's based on where it is compared to the Earth. So if you have a ball that's high above the Earth compared to a ball that's low compared to the Earth, the ball that's higher has more potential energy gravitational because it can fall farther and be influenced by gravity for a longer period of time. So it's going to have more potential energy gravitational. We can also have potential energy dealing with electrical fields, and we'll get to electrical energy in just a second. The next one we have is kinetic energy. Kinetic energy is a portion of energy associated with motion of a body. So anytime an object is in motion, it has kinetic energy. In physics, we talk about kinetic energy being used by the equation mass times velocity squared. So the amount of mass we have has a huge influence on the amount of kinetic energy we have. If we have a really large object, it could have a lot of kinetic energy. If we have a small object, it could have a lot of kinetic energy depending upon how fast it's going. And then velocity squared so how fast it's going has a huge impact on the amount of kinetic energy it has. The next type of energy we're going to deal with is chemical energy. And chemical energy is released as a result of chemical reactions. So you put two chemical reactions together, they make an explosion. That's chemical energy that's being released. The next energy that we have is electrical energy. So electrical energy is a form of energy related to the position of an electric charge in an electric field. When we talk about electric charge, we're talking about positive and negative charges. Like electrons are negatively charged, protons are positively charged. So where those guys are in an electric field, and anything that has an electric charge is going to set up an electric field. Wherever those are, they're going to have amount of electric energy. And if we want to think about if we have two charges that are alike, two positive charges, those are going to be repelled from each other. So they're going to have energy that wants to push them away from each other. If we have a positive proton and a negative electron, those are going to be attracted together, so those are going to want to come together and collide. So that's electrical energy. Next we have thermal energy, and this is also considered heat. So when we talk about thermal energy, we're talking about the energy. Thermal energy is a kinetic energy due to disordered motions and vibrations of microscopic particles. So the hotter a substance is, the more the molecules are moving around. So they have a lot of kinetic energy when there's a lot of heat involved. So the more energy, thermal energy they have, the more kinetic energy each of the particles has. So that's thermal energy or heat. The next one that we have is nuclear energy. So if we have a nuclear reaction, energy is going to be released. So in a nuclear reactor, we have a chain reaction being set up, and energy is being released because we have nuclear decay, and that's going to be nuclear energy that's going to be released. Or if we drop a nuclear bomb, we're going to have a whole lot of nuclear energy released. And the last type of energy that we're going to look at is electromagnetic energy. And this is a wave characterized by variations in electric and magnetic field. The easiest way to look at this is light. Light is an electromagnetic energy. When light is interacting with your eye, it's transferring energy to your eye so that you can see what it is bouncing off of. And the electromagnetic spectrum, light, is composed of an electric field and a magnetic field that are perpendicular to each other that keep varying with each other. So that's what light is. And we'll talk more about light when we get to a little bit of the electromagnetic spectrum. The next piece we're going to look at is Einstein's mass-energy equivalence. This is the famous equation, E equals mc squared, where E is the amount of energy that's there in joules or electron volts. Mass is for m, and that's going to be measured in kilograms for the most part. And c is the speed of light, and the speed of light is 3 times 10 to the 8th meters per second. And since we're a metric country, we're going to use 3 times 10 to the 8th meters per second. And if you have a little bit of mass, that could transfer into a lot of energy if you can harness that energy. When you deal with nuclear reactions, you're dealing with that law, and that's the amount of, when you lose that amount of mass, you're going to gain a whole bunch of energy. The energy is going to come in a couple forms. One is radiation. Radiation is energy that comes from a source and travels through some material or through space. So radiation we can think of as light, heat, sound. Those are all radiation. And when a person gets exposed to radiation, we get irradiated. So one way that we're going to get irradiated, and what you guys are going to do in radiation physics, is when you take an X-ray. That's light. That's a form of light. You could possibly get irradiated, and you want to limit the dose that you guys get, limit the dose the patient gets, and that's what you're going to be studying in some of your other classes, is how to limit that amount of radiation that you or your patients are being exposed to. When we talk about X-rays, we're talking about ionizing radiation. So we need to ionize some tungsten so that when the electron comes back into the lowest shell, it gives off X-rays. And so we actually want some ionizing radiation in here. And there's some basic ways that we can get ionizing radiation. One is alpha particles, which are basically helium nuclei. And those are fairly big, and they can have create a lot of ionizing radiation. Beta particles, which are electrons. And that's actually what we're going to be doing when we have X-rays, is we're going to be streaming some electrons at a tungsten atom, and we'll have some ionizing radiation that way. Neutrons could also be ionizing radiation, and gamma rays, which are high-frequency electromagnetic waves. X-rays can also be ionizing because they have high energy as well. Next thing we want to look at is some fundamental particles that we have. And we have 3 fundamental particles in this class that we're going to deal with. The electron, the proton, and the neutron. And they are all in the nucleus and in the shell around an atom. And the first one we're going to look at is an electron. And we need to know the mass of an electron, which is 9.109 times 10 to the negative 31 kilograms. It's very light. It's not very heavy at all. But it has a charge, which we'll get to in a second. And then it has an AMU, an atomic mass unit, that we'll talk about in a second, of 0.000549. And in chemistry, we use atomic mass units a lot. In physics, we use the mass of the electron, the 9.109 times 10 to the negative 31 kilograms. And it also has a charge. In physics, we use the charge of the electron to be a negative 1.602 times 10 to the negative 19th coulombs. Coulombs is just a way of measuring charge. And coulombs are actually very large. So that's why the charge of an electron is very small. In chemistry, you would use the charge of negative 1. I'm a physicist, so I use the negative 1.602 times 10 to the negative 19th coulombs as my charge. I hardly ever use negative 1. And then we have to have a way of showing what the symbol is. And the symbol is lowercase m and then a subscript of e. So m sub e is the electron. The next subatomic particle we're going to look at, or fundamental particle, is the proton. This one has a mass of 1.673 times 10 to the negative 27th kilograms. It is much, much more massive than the electron. They all sound like they're very small, negative 27th and negative 31, but it's 4 magnitudes bigger than the electron. And so the AMU, the atomic mass unit, is 1.00728 atomic mass units. And it, oddly enough, it has the same charge, except positive, as the electron. So the charge of a proton is 1.602 times 10 to the negative 19th coulombs. And therefore, in chemistry, they use a charge of 1. Symbol for proton is M sub p. So M sub p is a symbol for the proton. The last fundamental particle that we have is the neutron. The neutron is in the nucleus of an atom, and it has a mass of 1.675, so almost what it is for the proton, times 10 to the negative 27th kilograms. The proton and neutron have about the same mass. The neutron's just slightly heavier, but not much. So it has an atomic mass unit of 1.00867. But oddly enough, it doesn't have a charge. It is a neutral, that's why neutron, a neutral particle. It doesn't have a charge on it. And the symbol is M sub n on that. Now the atomic mass unit is the unit of mass equal to 1/12 the mass of an atom of a carbon isotope with a mass number 12. So basically they needed to have an easier way of figuring out the mass of a atom or the mass of some chemicals, and so carbon was a very abundant chemical element, and so they decided to do 1/12 the mass of a carbon. That's why carbon is 12. And the atomic mass unit has a mass of approximately 1.66 times 10 to the negative 27th kilogram. So it's almost the mass of a proton, almost the mass of a neutron.